So welcome to another edition of our Liftoff webinar series. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs with LIFT. Today, we are happy to welcome ARRIS Composites to speak with us about some breakthroughs they have in advanced composites and some topology optimized lightweight structures. So Ethan and Riley will share their presentation and information with us a little bit shortly. I do have a few housekeeping items for folks, though. If everyone's not on mute, please go ahead and mute yourself. Everyone should be on mute. But we are recording this webinar. It will be available on our website at lift.technology later on today or probably tomorrow. So we want to make sure that all the background noise is kept at a minimum. So please keep yourselves on mute if at all possible. We will be having a Q&A session at the end of the presentation today. So please use the Q&A function that's available on the Zoom taskbar at the top of your screen. I know we are all very familiar with these virtual platforms and Zoom and all the other platforms that are out there as we continue to go through this pandemic. So hopefully everyone is safe and well, but please use the Q&A function and I will facilitate that at the end of the presentation. So I do want to take a couple of minutes and share a little bit about LIFT for those who may not know who we are and what we do. LIFT is a Department of Defense National Manufacturing Innovation Institute. We are part of the larger Manufacturing USA network, so one of 16 National Manufacturing Innovation Institutes around the country. And our mission is to drive American manufacturing into the future through technology and talent development, which is why we have folks like ARRIS as members of LIFT. We are a nonprofit membership-based organization. And we believe that smarter manufacturing is the future of our national economic security and resiliency. And the next area, the next region that takes advantage of smarter manufacturing is going to come out ahead. And we want that to be the USA. So what do we mean by smarter manufacturing? We mean the connection of materials, processes, systems, and talent, the talent that runs underneath all of those. There's great ideas and wonderful innovations out there, but if you don't have the talent to help work them, then you're going to be at a loss. So we're talking about various materials, various processes being implemented in systems around the manufacturing sector, again, which is why we have ARRIS on board going to talk to us about composites and so new processes they have and a project actually that we are working on with them. So at LIFT, we have two programs: technology program, leading innovations for tomorrow, and our talent program, learning innovations for tomorrow. So a little bit about our talent program. We have four main pillars of technology, all the way from ICME, integrated computational materials engineering, to agile and smarter manufacturing, to alloy and process development, multi-material joining. All of these are areas of focus in which we work. A little bit deeper dive here on the screen. You can see all the different avenues and different project areas that we work on underneath those pillars. So you can imagine there's a lot of work going on in our ecosystem focused on these pillars. Any questions about LIFT or technology? Please again visit our website at lift.technology. You can reach us there directly, and we'll be happy to talk to you about a little bit more about what we do on the technology side. On the talent side, again, it's all about innovation, new learning tools, pathways, and venues, kind of revolving around our Ignite Mastering Manufacturing curriculum, which is a high school curriculum, 3-year program that high school students participate in around the country, actually. But we do host it at our LIFT Learning Lab as well, which is in our Detroit facility, overlooking our high bay. So not only do students come in to participate in the Ignite curriculum and get some hands-on experience with material science and pneumatics, electronics, smart manufacturing, all of those things, just to see what manufacturing looks like in the year 2021, but they get to look out on our high bay floor and see our technicians hard at work with innovations that our members are currently working on. We also offer world-class certification programs in jobs that are available today: CNC, welding, industrial technology maintenance, robotics. Offer that via our LIFT certified program, as well as a program called Operation Next, which is one we are most proud of for active duty men and women in the military. Before they leave the service, we give them the opportunity to earn a credential in one of those in-demand jobs. So not only do they leave the base and get on to their next operation, their civilian career, but they walk out of the gates with a in-demand, industry-recognized, nationally portable credential that they can go get a job immediately. And that program has been expanding across the country. It's available to the National Guard and Reserve in Michigan, Florida, Wisconsin, and also available at Fort Campbell, Kentucky. And stay tuned for a future announcement on another base later on this year. So we're excited about that program. So I mentioned LIFT is a membership organization. So what do you get from being a LIFT member? Well, all the things you see on the screen, from being a trusted advisor, helping people turn the corner with smarter manufacturing, technology accelerator, taking technology innovations from concept to commercialization, technology showcase, invites you to visit our 100,000 square foot facility you see behind me in Detroit, showing you the art of the possible with smarter manufacturing. We're a connector and convener, which is why we're all here today. A talent developer, spoke with you about that already. And finally, we are a government partner, helping folks get involved with the federal government and eliminate the barriers that often stand in the way of getting involved with an organization like that. So please, if you have questions, reach out to us, follow us on our social channels. We would invite you to do that. You can call us on the phone like olden times. You can use your email. You can visit us on the website. We'd be happy to speak with you. So that is LIFT in a nutshell, but I'm going to stop sharing my screen and I'm going to turn it over to Ethan and Riley from ARRIS Composites to talk to us about what they're working on. So gentlemen, the show is yours. And you are
great.
still
Thank you, Joe. I will share my screen, and
perfect.
With any luck, it's coming through now.
Yep, I got you with Carl and Jeff on the cover there.
Perfect. So I thought I'd lead off with these quotes just to set the landscape a little bit. Carl here in his quote speaking to a little bit of the performance of advanced composites and the potential for impacting broader industries, broader applications than it had been applied to, than these materials had been applied to, has really been a effort of many organizations, as well as a whole variety of government programs. And then Jeff Immolt's quote here, who we had a great opportunity to meet early on in the company as well. And from his vantage point in GE, running GE, he actually shared his origin story, where he had started in GE Plastics when they were introducing the chopped fiber composite pellets to the injection molding industry. And this was a major uptick in the use of composites in automotive. And in the 1980s, when adoption was really became very, very, very broad, the actual product architecture can be seen to shift. Those non-structural metals of the 60s and 70s gave way to the more integrated, streamlined designs of the molded materials that came after that. And a significant number of benefits that came along with it. But with that, those chopped fibers essentially pushed the plastic space a little bit up into the right of this stiffness to weight, strength to weight ratio chart, giving plastics the ability to move into some of the spaces where you'd have aluminum and some of the metals and the non-structural parts. However, many of the composite, of advanced composites, whether it's sheet materials or aligned fiber materials, were really, the cost of many of those manufacturing methods were out of reach for the larger mass market industries. And we won't go through this in a lot of detail, but the important point here with this overview of the composites landscape is that, these technologies on the top row that had greater design latitude to make the valuable parts that carried load paths through all three dimensions really had lower strength, whereas many of the higher strength methods on the bottom row have significant design limitations associated with them. So this is really the space that we came into, where we're looking at these feedstocks that are typically used in the continuous fiber world. And this, looking at these feedstocks, this was really kind of in the backdrop of this kind of renaissance of structural design, where topology optimization and kind of these academically ideal designs were being really popularized by the 3D printing industry. However, the manufacturing methods, primarily working with pure resins or pure metals, were not the really best material for these lightweight structural designs. And the challenge kind of revolves around, we use the grain of a tree to demonstrate anisotropic materials, these orthotropic composites, and how intuitively we all know how the grain of a tree follows the load paths that the branches and the boughs face. And the challenge in complex composite structures is running the fibers through that is not really practical today. And this is really where we developed our manufacturing method to enable the use of these continuous fiber materials, but aligning them along the stress loading paths within these complex parts, and in particular, these topology optimized parts, where you're getting the best out of both worlds, the best of the structural design world and the best out of the materials world. And this is a image of the actual part that was in that animation. And what I'm going to do is hand the presentation for a couple slides here to our CTO and material scientist by training, Riley Reese, to speak a little bit about the work that we've done with a few customers and how we do this. So Riley, are you?
Yeah, sure.
You have
so
audio?
First,
Yep,
let's like to start with this Northrop Grumman study. So we had a kind of detailed paper that we published in collaboration with Northrop Grumman at CAMEX. It really goes through the first phase of kind of design optimization and the anisotropic topology optimization that we developed here at ARRIS that gives us the ideal shapes for continuous fiber composites. And then here you just see the kind of end of the paper, which shows that some of the experimental results that we did around this benchmark part that Northrop Grumman had. So the top left was the design they start with. It's a 3D printed T design. That's their baseline. So we redesigned it, taking advantage of the load conditions and the ideal fiber alignment, made these brackets with our process, and we were able to match the stiffness of the titanium bracket. You can see the slope of the lines are the same. Our line is the blue line. And then we were able to do that, but remove 80% of the weight of that original bracket. So you're left with a structure that's 20% of the weight of that original bracket, yet has the same stiffness, and the huge kind of jump in performance is something that really is unrivaled when you look across the capabilities in other manufacturing tech. We had a similar exercise that we did with Airbus as well, and we took this bracket that was 220 grams. You can see our final bracket on the right. Their bracket was actually an assembly and a bit more complex. We were able to take their original bracket, take out 75% of the weight, and we did a study to really look at not just the performance benefit or weight savings that you get from fuel, but the impact that this has on the environment. And so when you do just some rough numbers around this, you find that just taking this bracket and implementing this bracket on one version of the Airbus aircraft, it's the A350, and you take it over the lifetime of those planes flying for aircraft made in just 1 year, and you end up removing 357 million metric tons of CO2 emissions, and that's equivalent to 22 million U.S. persons emissions in a year, or equivalent to 0.75% of worldwide emissions in a year. And so what would at first seem insignificant actually makes a pretty significant chunk of savings, both in fuel and CO2 emissions. And this is just the start of what technology we can bring to aerospace and lightweighting.
So I'll do a kind of hard pivot here, where we were talking about aerospace with the last two case studies. And one of the important things is, while we can be our additive molding technology that we'll look at in a minute can be applied to these more high mix manufacturing environments, we are able to our systems can be configured for higher volume production as well. And we'll talk about that in a little bit more detail. But the thing about working with the consumer products and sporting goods and drone companies that we are is the speed with which they can get products to market, and the ability to innovate in more disruptive ways. The two bracket examples that we looked at are drop-in replacements that significantly outperform the existing component. And in some of these areas, in products that have very long life cycles, the drop-in replacement is the practical solution for us to look at first products in market. However, in a space like drones, where there is a lot more latitude for innovation and a lot shorter design cycle, we can do things that are far more disruptive. And this becomes a little bit better illustration of what we can look at in terms of product architecture, since we've looked at just the pure performance around structural elements. So Skydio won the Consumer Electronics Show Innovation Awards for this X2 drone. A significant portion of their marketing up into this product launch related to this case study. That I will show you here, about how they significantly altered their design based on the state of the art in manufacturing, and took advantage of our design latitude to make a drone aerostructure that significantly outperformed what had been possible before. So consolidating 17 parts into one, 25% lighter, but also increasing strength, stiffness, and durability at the same time as reducing weight. And quite novel is the use of an antenna window within a complex structure like this, where there have been antenna windows, used for decades in aerospace. There hasn't been really a cost-effective way to scale production of these advanced composite parts for these higher volume applications. In particular, doing so with the design complexity and the composite material capabilities that our methods enable. And particularly noteworthy for any kind of structures that move, whether it's vehicles or aircraft, is using these aligned continuous carbon fiber materials through open structure lattices, like are on the top of the part, but also in the structure of the sheet material. We're calling this a ribbon sheet structure, where you have the ribs reinforcing the sheet material in that bottom area, and then you have distinctly different properties of the glass fiber and carbon fiber. So you're achieving a variety of functional requirements within the part. Also, after we achieved all the engineering requirements, the industrial design team was able to take some of the best in class in mold finishing design latitudes to design this kind of beautiful industrial design for that really became the brand identity of the product. And by using tool finishing techniques, every part that we have come out of our additive molding tool, takes on this really just beautiful look, without any kind of post-processing or substantial cost associated with the post-processing that has really characterized most of the advanced, a lot of the additive manufacturing technologies, and has been a barrier to the post-machining and post-processing and finishing. So the way the technology works, we'll go over a couple slides here, but at a high level, these three buckets are the primary drivers of value. So starting from the bottom, material scalability really comes from we're standing on the shoulders of great innovators in the resin and fiber world that have pushed forward the thermoplastic composites that we work with, both in the aerospace materials. So the bracket that we showed earlier here, for those of you that have worked with the aerospace grade materials, you'll recognize that ring of the aerospace grade peak carbon fiber. And then when you look at the resin systems that we use for these consumer products, that have a much lower cost point, but also there's been a substantial amount of work that's been done for the cosmetics and driving the cost performance profile of those consumer and automotive grade resins higher and higher as the injection molding world has really demanded such high volumes of these materials. So, material, each one of these three areas we could talk about in great depth. I'll hit on them pretty quickly here, though. Machine scalability, the modularity of our manufacturing systems that enables us to put our systems in high mix manufacturing environments that aerospace production requires, as well as high volume end-to-end automated environments that the high volume consumer product customers require, is a key element of our manufacturing systems. And then product performance, as we had really talked about through the previous case studies, the value of these stress vector aligned fibers that is similar in principle to what you see in automated tape layup, but being able to do so within complex shapes within all three axes. And doing that within those unique shapes, and doing so with different materials, is quite important. So purely, we'll typically look at two types of applications: things that are purely pursuing structure, where we have a load to carry through a white space, and then things that might have a bit more of a limited design envelope for us to work within. So examples of that might be consumer electronic, as in the case of watches, or portable electronics, or things where there is a very set geometry that we have to work with. And within that, we might have just millimeters of design latitude in certain areas. So with that, we typically will define a set of requirements, and Riley's team, and Riley, I don't know if you're able to speak through this right now, but Riley's team has developed our software tools that have and collaborate with our customers on these collaborations. So let me have you actually speak through this.
Yeah, so this kind of outlines the steps in the software process that that effectively kind of constitute the really the sum of what we can do around optimal design for composites. And so in the best case, we can start with requirements from the customer, both geometric requirements in terms of where the part is mating or interfacing with other sections that are fixed boundaries, and then where we have freedom to design, and then the mechanical requirements around where the load cases are on that part. So with load cases and with boundary conditions, we can then run through our topology optimization. And unlike standard top-opt, which just solves for density based on load conditions, we're solving for both density and fiber orientation simultaneously. And in doing so, we get different structures than you would get with conventional topology optimization. So this generates us basically the rubric or the tool in which we know what ideal fiber alignment should be in each specific mesh of this CAD file. And what we do is we take that and create then our preforming instructions. And so from the ideal fiber alignment, we're able to break up the part into discrete units of preforms that we manufacture that are brought together to create the final object with the ideal fiber alignment. We then can do computer simulation of the end part, looking at the stress in the part where the concentrations are, and kind of verifying that the design we ended with is adequately addressing the load case. And then we lock the design and send it over to manufacturing, where we run through, where we use this software actually to drive this manufacturing process that you see. And so we start with the raw materials in-house. We work with thermoplastic polymers and a variety of fibers. And so starting with the raw materials, we impregnate the raw materials together to create the prepreg that then goes through this shaping process where the prepregs are formed into preformed composites, and the piece is then assembled. So you get this near net shape that they can then be placed quickly into a tool where the mold processing under heat and pressure consolidates that part, giving you a very low void content, giving you kind of the full structure and distribution of the resin and fiber in the final part, and ultimately deriving the surface finishes Ethan was talking about with Skydio. And so then through this process, we can bring, you know, this continuous fiber capability into mass production.
Right. I don't know if you can see the question up here, and while I would hold questions maybe towards the end, this would probably be a really appropriate time to address it if you can see it.
Okay.
Oh, actually, it's not showing up. It's just showing up on mine. So is the
optimizer? No, I see it
optimizer?
from Ryan. Yeah.
Okay.
Is the optimizer including fiber alignment as a design variable and calculating sensitivities along the density variables, or are they set is equal to local principal stress directions at each iteration? Yeah. So the fiber alignments are set based on the local principal stress directions of the mesh at each iteration. So we start with all the fiber pointing in one direction, and then through the iterative approach, the fibers are reorienting themselves to align against that principal stress direction. And then we run the simulation until, right, ultimately we're seeing very little movement in the fiber alignment, and then we'll stop it at that point.
So when we look at a lot of the legacy designs, I think everybody's pretty familiar with the structures underneath the skin. And when you look at, you know, some of the concepts without manufacturing compromise, you typically are getting to these almost more topology optimized shapes that are impractical given existing manufacturing limitations. And so this is a rather wordy slide, but I think the important takeaway is a bit of kind of mechanical engineering 101, that as you increase the thickness of these optimal stiffness structures, like in the case of honeycomb laminates or trusses and I-beams and some of these different profile shape beams, that you are increasing stiffness exponentially, where increasing weight and material usage only goes up at fractions of a percent in these cases. So the reason you see on many of the largest structures open structures, but on beams in a typical building are closed structures, is the cost of really judicious use of material. The cost of making that open structure does not outweigh the value that it delivers. So that's why there are so many of these closed cross-section beams in the world of metal. And these closed cross-section composite beams also, because of the existing production technologies, are used more broadly than open structures. However, the open structures have a number of advantages that are kind of laid out here. One of the big ones for a lot of vehicle applications is as you take a closed cross section to a greater thickness, all of the walls get thinner and thinner, and this becomes a challenge, unpredictable around buckling. And while that happens with is a consideration around all materials, it is particularly challenging when you look at composite materials. Here you can see by concentrating more of that unidirectional material, in long runs, you have naturally tougher structures, and you can increase the thickness without creating these delicate thin-walled structures. So when we look at taking those open structures and combining them with the sheets of material or the windshields that are over just about any vehicle or thing that flies, you have this ribbon sheet type structure. And this chart is simply showing how you have these three dimensions: the thickness of the material, and that sheet material is really what kind of monocoque, like composite monocoque design has really been built around, is carrying the structural loads through the sheet of material. However, you can see that approach has its limitations, as that blue Y dimension does not drive the specific stiffness of the structure as much as the rib does. And it's actually not the width of the rib, that X dimension, it's the height of the rib. And this all goes back to the previous slide, that thickness is so important in driving stiffness. So our ability to make the complex ribs on the backside of continuous composite or continuous other types of material. In this case, this is a continuous ribs on a continuous sheet of metal material. Really allows us to take advantage of that red dimension, the thickness that drives the specific stiffness of anything optimally. So with regard to, we're really kind of purely looking at some of the mechanical design requirements. If we pivot and look at what you can do with multiple materials, we have a couple slides that speak to that. And the important area that this focuses on is the fact that we are an additive technology. And while the previous slides were speaking to our approach of using aligned composite materials and additively building up those materials so we have the aligned fibers in the right areas. The other benefit of using that additive process is that we can switch out the materials, as in the glass fiber antenna window example that we had before. But there's a whole variety of other functional requirements that might be served with this. And a lot of the pioneering work for these applications have been done over the decades in aerospace and DoD, taking advantage of a wide variety of different composite materials and embedding those composite materials for a whole variety of functions. And this idea that with our ability to put these different materials into different complex single parts allows us to meet a variety of functional requirements that are typically done through different components that are made in an assembly, whether it's the antenna window or damping, vibration absorption, tough areas, stiff areas, a wide variety, and shielding is obviously a big one as well. And we're really at a moment where these capabilities are very exciting for many of our customers that are taking the connectivity into a whole variety of devices and vehicles. I think everybody is probably very acutely aware of the whole concepts, all the concepts around IoT in a variety of industries. So never has there been a greater importance associated with antenna performance within very compact structures that are highly ruggedized. And many of the business models around these IoT type devices really require the incredible, chemical resistance and environmental ruggedness and lightweight, which typically is a key important element of many of the business models for these customers. Also, last piece, kind of wrapping up, and then we'll just talk about a couple markets and finish up our presentation here, is for many of our customers, sustainability is a significant element considered in next generation products. Obviously, in the world of consumer products, the way they look at sustainability and their life cycle analysis is quite different from the aerospace world. So, case in point, that third step product life, in the case that Riley gave earlier, lightweighting the Airbus bracket that Riley was pointing out earlier has a huge value in terms of sustainability. But that part might be installed, for have an effective life, well over a decade. And so, the recycling is not something that is as much a driver in the life cycle analysis as the product life. But for some of our consumer product customers, the ability to take composites for the first time and really recycle them efficiently, where previously you would have needed pyrolysis to burn off resin systems, and there weren't really kind of well-organized kind of recycling programs for these, is a significant pain point that limited adoption, that with some of the novel recycling methods that we're working with them on really opens up some of their sustainability objectives, as well as the performance areas that we've talked about. So with that, we can look at a few of the different kind of industries that we work with, and we really see some of these ideas around key capabilities that frequently identify great applications for us, where we can find a really good new way of doing something. This just lists off some of them that we've touched on here: the part consolidation, performance drives commercial value, multiple materials drive a more compact package or a more compact, higher performance device. So this really hits on some of those primary topics that drive all of the different that are good starting point questions for the variety of industries that we might work with. So we really have two distinctly different areas of the company. The consumer products and a lot of consumer electronics, and we have a lot of the new product introduction and prototype work for that done at ARRIS US in California, and we do have production here, but we also have production in Taiwan, where we have set up the facility for many of our customers that are doing assembly in Asia and required in-region production for their supply chain requirements. When we're shipping thousands of these parts at a very high frequency, their supply chain requirements require a more compact footprint. So we offer that service as well as domestic production for some of the customers, like Skydio is a great example of a company that that has brought great drone production back to the U.S. and reshored and developed a great product meeting a global demand as well as U.S. Government requirements. So with regards to vehicle and industrial, similarly, we work with the prototyping and development work out of our U.S. facility. Obviously, we have our partnership with Lyft as well. And for production phase, we do have production partners that we will be announcing in the 2023 timeframe in these other areas, as there are obviously great leaders in these different industries that would be the key partners that we would work with on those. So this just gives you this is the California NPI and R&D Center image of that here jumping through. This is the ARRIS Taiwan, which is essentially the world's first mass production facility that is actually contract manufacturing these next generation products using our additive molding manufacturing systems. And this production facility is set up primarily with high volume production setups where ARRIS US has a lot more of the high mix NPI type systems. So that is an overview with the expertise in manufacturing that we have on the phone. We could probably take this amount of time on one of a few dozen different topics that we only scratch the surface on here, but I certainly thank Lyft for the opportunity to speak to everyone, and we're happy to answer any questions.
Hey, we appreciate that. Thank you so much for the presentation and introduction, and folks on the line can understand why ARRIS and Lyft have partnered. As I mentioned at the beginning, our view of things in terms of connecting materials, processes, and systems. I think you saw that run through this presentation here. Couple questions have come up, and one that I wanted to ask, and I've asked this of people previously as it relates to different materials that they're speaking on or different processes they're speaking on. What kind of how do you determine, what decision process do you go through in terms of when to use, say, the composite techniques that you were talking about versus, obviously that's your business, so you want to employ that as often as possible, but how often would you say, that's probably that, maybe this is not the best route to go for whatever component someone is trying to make? How do you walk through that process and that decision making?
Yeah, it's a great question, and it is something that we spend a good amount of time every day looking at around any potential collaborations. We're always the first to tell our customer. We have manufacturing technologists from the conventional, from the additive world. We're the first to tell somebody when there's a better way than our ways to do something. We're always looking for something that has significant commercial advantage for the partner or customer that we're working with. And in the grand scheme of like real production parts, for something to go to production, it has to just make sense. And the earlier you determine it doesn't make sense, the less of that relationship capital you've used up working on the wrong problem. So with that, we definitely have a variety of case studies and things that we work with, and we're adding more and more to the website. But purely, if we think about it in terms of the commercial advantage, that can actually look like a number of different things in a variety of industries. When it's kind of a pure structural bracket, right? It's very easy to demonstrate value proposition there. It gets a little bit murkier. Skydio, I think, is an excellent example of where, they not only had all of those engineering benefits, but there was an incredible thought leadership and innovator story that went along with doing all of those things that had substantial commercial advantage associated with it. And, they won the Consumer Electronics Show Innovation Awards, and, a few quarters later was, we're valued at over $1 billion, and, we're the first US drone unicorn. So So I'm kind of hitting at different ends of the spectrum in terms of what value looks like. But the important topic here is that there's always inertia to do what's done before. Supply chain would much rather do what was done for the previous 5 generations. And the only way you jump out of that rut and is if there's a substantial value to taking on the added cost of doing something different. We've been showing kind of primarily small parts. I mean, this is kind of made in one manufacturing step with additive molding. We showed some simulations of these larger structures, but the neat thing about these large structures is that you've kind of got continuous fibers, running all the way from one end to the other, and taking advantage of the upper right corner of that strength to weight and stiffness to weight material data sheet that everybody's looked at forever in the composites world, but actually applying those properties to these complex structures. They're notoriously, when you try and make things with composites in the past, you look at the data sheet and then you make a structure, and the structure doesn't work as well as you would hope, because you can't follow those load paths. So while that part I just showed was 8 feet long, because we are using presses, there's typically a balancing act that we'll look at with regard to how big is practical. Typically, we like doing large part consolidations because we're eliminating all those discrete manufacturing steps, and then the assembly line of steps that then has to assemble all those processes. And all of those high tolerance manufacturing methods and assembly methods, carry costs. So large part consolidations are advantageous. But then when you get too crazy, it could, there's typically a sweet spot of large sub-assemblies when we're starting to talk about large vehicles that we can look at. But the key part is that you can have very high tolerance parts coming out. All of these holes are as molded with dead on accuracy. I think everybody on the phone probably knows the tooling world well, and the important thing with these near zero CTE parts with continuous fibers is that you don't have a lot of the kind of shrinkage and kind of warping issues that you will typically have with larger molded parts.
So it sounds like you moved on to the 2 questions that were asked related to size. I had an internet hiccup there, so I apologize for that. But sounds like you were talking about the size and the sweet spot of where you guys were, and if there are limitations to your manufacturing process now in terms of size. Is that where we landed?
Yeah, and regarding the last question, so Riley's team software is always improving and trying to converge on that perfect solution, first time off. Now that doesn't happen. There's always kind of the empirical that comes after the simulation, and we actually take a lot of that feedback to inform our software. It's one of the key elements that we've driven over the years to improve our prediction. However, because we are an additive process, we can iterate the fiber alignment design in very small, subtle ways. So it's not at all uncommon for us to provide a customer with their first articles with 3 variations, the sweet spot in the middle, and then bracketed on 2 sides that we want to get their feedback and make sure that we converged on the optimum for their requirement. So in general, the simpler the load path, the more limited the number of load scenarios we're trying to optimize for, the less the less iterations. The larger, the more complex, the greater the number of load scenarios we're trying to simultaneously meet meet the demands of, the harder, the more complex, and probably the more iterations you might expect.
Excellent. I encourage folks to reach out to these guys via the email you see on your screen now. If you have further questions and comments, or want to explore that a little bit more, we have a couple minutes left. So I wondered if you guys can touch on the project we are working on together a little bit at all, and just some quick highlights there regarding the seats and military vehicles.
Yeah, no, that it's actually a great transition, and let me hit the last question that David asked. Are there architectures that we can't achieve? And I'd go back to what we were saying earlier. There's always things that we can't and shouldn't be doing because something else, might be able to do it. That said, we have a pretty huge amount of latitude in terms of a new manufacturing method. We have a lot of folks on our team that have, worked in the additive world pretty extensively. And, what you see in a lot of the new additive technologies is that there might be a really narrow slice of killer applications for a particular company or for a particular technology. We certainly have a lot more breadth, but we're not so presumptuous to think we can make everything in the world. But if we start looking at vehicle architectures, is where there's many exciting opportunities, really, because a lot of the existing methods really have resulted in compromises that are significantly different from the structural ideals. So you look at, and this is where kind of working with Lyft has just been a really awesome synergy, where they're really looking at where the U.S. auto industry can potentially be more competitive by exploring the architectures that might be just over the horizon, but no single company has shouldered the responsibility of looking what's just over the horizon. And you look at the major shifts in automotive architectures, and they come and go, not at a great speed, because once you're all tooled up and all of your thousands of engineers know how to make some things a certain way, and you have your supply chain making things a certain way, it's difficult to deviate from that. The great thing about seats as a starting point is, while we could talk about a whole variety of things in the architecture, seats are actually a more practical area to look at changing up architecture and getting a benefit. First, it's a common application across every vehicle, whether it's cars, planes, trains, automobiles, or military vehicles, and all of them have the same fundamental need. So with that, you essentially have you have the bottom of the car the seat's sitting in, and then you kind of have the perpendicular axis that you have to have have a back. And so with that, we open up really working within that z-axis, aligning fibers from a horizontal XY plane up into a z-axis in very novel ways. So we talked a lot about these brackets, where we've done very similar things as this, where we've taken essentially an XY. I don't know if you can still see me. Where we've taken something that's bolted in the XY plane here, and then we've run fibers up into that z-axis. And in a very similar way, we've taken open structures, as in the case of the truss that we've talked about here, which is essentially an optimal beam. So you take the ability to make that joint and the ability to make an optimal beam that is connected to that joint together, and you really have a set of strategies to solve the very common need of holding a seat back up, given the variety of load scenarios that seats in a whole variety of different vehicles might require. So with that, I think Joe provides kind of a quick overview on what we're targeting. Obviously, when you think about military vehicles and the value to have greater range, the value to be able to take more gear, take more equipment, especially when you're starting to look at vehicles that have a whole bunch of passengers and then a whole bunch of mass as it relates to safely seating those passengers. The Army essentially becomes the strategic advantages for the Army become really clear. However, you can also see how many of those requirements are broadly shared by any vehicle that carries passengers.
Right. Well, thank you very much for that quick overview. I did want to touch on that project really quickly, but I do want to be cognizant of folks' time. So please, again, this webinar will be has been recorded, will be posted at lift.technology later on today or tomorrow morning. If you have questions, please reach out to ARRIS directly or reach out to us, and we can certainly get you in contact. And then stay tuned for future webinars. In 2 weeks, we have our friends from Mala speaking about powertrain cooling solutions. So stay tuned to your emails for that. I want to thank ARRIS, thank Ethan, thank Riley and your team for your presentation today and your membership and partnership with Lyft. As folks heard, we're doing some cool stuff together. So we're looking forward to continuing that going forward. And thank you everyone for joining today.
Thanks, Joe.
Thanks, everybody. We'll talk to you
Yeah,
next time.
thanks for your time. Bye-bye.